Hello students, we're on notes number 1 and we're going to review vocabulary, notation, and so on. Lots of things that we're looking at today just to review some of the things we've learned in previous math classes and be ready for calculus. Some of these we talked about in our Zoom meeting. So this first slide contains different sets of numbers. We have the natural numbers, which are also known as the counting numbers. Now, I don't often use the symbol, but there is a symbol, this N with a double bar on it. And the counting numbers, or the natural numbers, is the set of numbers starting with 1, and then 2, and then 3, and so on. The integers would be the set of counting numbers and their opposites and 0. And the integers can be represented with a Z with a double line. So I'm just going to put ... -3, -2, -1, 0, 1, 2, 3, and so on. Rational numbers are numbers that you can write as a fraction of an integer over an integer. So can write as a over b, where a and b are integers, and because we can't divide by 0, and b is not equal to 0. So that could be, for example, 7 over 2. So think of it as a fraction. That could be 19 over 1,000. Think of it as a fraction. When you see the word rational, think of the root being ratio, and ratio is fraction. However, you could also have something like 7 over 1, but you would probably just see it as 7, so it might not look like a fraction. But if it can be written as a fraction, even if it isn't originally written that way, if it can be written as a over b, where a and b are integers and b is not 0, then it is rational. If it's written in decimal form, and it's rational, it's either going to terminate or repeat. For example, if you have 1/4 and you write it in decimal form, you would have 0.25, that terminates. Or if you have 1/3 and you write it in decimal form, you get 0.33333 repeating. So both of those are rational. We also have irrational numbers. These are numbers that you cannot write as a fraction a over b, but irrational numbers have to be real and rational numbers have to be real. And our real number symbol we typically write with a double bar on the straight part. Your book just has a bold R. Okay, it doesn't put the double line, it just makes it bold. So you'll notice that in there sometimes. Real numbers are the numbers you can map to a number line. We could also say that it's the set of all of the rational numbers union all of the irrational numbers. Union means it's in one set or the other set. What's the word I'm looking for? Actually, union means one or the other or both, but in this case, there's no way for a number to be both rational and irrational at the same time. Okay, now let's talk about intervals and sets, interval notation and set notation, and you already saw me using these symbols on the last slide. Those are called set braces. So we can put set braces around a set of numbers. When you see round or square brackets, those are used for intervals. If they're round, you're not including the endpoints. And if they're square, you are including the endpoints. And you see down below, you could have one that's half and half. Okay, if it's round and it's not including the endpoints, we call it an open interval. And if it has square brackets and it includes the endpoints, we call it a closed interval. So it can be semi-open, semi-closed. Okay, let's look at a few examples. So let's say we have the interval from -1 to 4. Now that looks like an ordered pair, but in the context of talking about intervals, it's not an ordered pair. It's not x comma y. It's a value of -1 through all real numbers to a value of +4. So on a number line that would look like this: -1, 4, all the way from there to there, not including the endpoints. Infinitely many values in that interval. To write that in set notation, we would have, let's say we're talking about x values, we would have -1 is less than x is less than 4. Or maybe it's y or something else. Let's look at an example of a closed interval. So suppose we have the closed interval from 6 to 20. So on a number line, you're including 6, you're including 20, closed circle, closed circle. And using set notation, that would look like 6 is less than or equal to x is less than or equal to 20. Here's an example of one that would be potentially half open, half closed. You could have something like this: the interval from 0 to infinity. Remember that infinity is not a finite number, so there's no way to include it. You can't actually reach it or get there. So there's no way to have an infinity with a square bracket on it. You always have to have round. And on a number line, that would look like that. And then with set notation, you would have x is greater than or equal to 0. You could also have, say, a half open interval that was something like -5 to 2. And so on a number line, you'd have an open circle at -5, a closed circle at 2, segment in between. There's infinitely many numbers in there. And using set notation, it would look like -5 is less than x is less than or equal to 2. Just like you can never have a square bracket around positive infinity, you could also never have a square bracket around negative infinity. Okay. So in class, we looked at this graph, and I just made this up, and we're calling it the graph that represents OSU student X's 24-hour COVID exposure risk level. So let's say student X over a 24-hour period had a risk level of 0 being the lowest, 10 being the highest. You can see the graph in between. And I've split it up into 4 different sections, A, B, C, and D. And in class, we kind of brainstormed what the student might be doing over the course of this day. What I want to do now is I want to use this graph to talk about functions, domain, range, increasing and decreasing. So is this the graph of a function? Well, remember, a function is a special kind of relation where every x value has exactly one y value, or every input has exactly one output. Not more than one. If it's an input, if it's in the domain, then it has only one and not more than one output. So the way we test it with a graph is the vertical line test. So if I pass a vertical line through anywhere in the graph, it can only pass through one point. Now notice that there are some places where I have an open circle and a closed circle in the same vertical line. Remember, the open circle does not count as a point and the closed circle does. So still that line only went through one point. The same thing over here, going through an open circle does not count as a point. So no matter where I draw that vertical line, it's only going through one point. Therefore, we do have a function. So this is a function. Okay. Its domain is the set of real number inputs. When we talk about domain and range, we talk about real numbers. Real number inputs that have real outputs, or that correspond to real outputs. So what's the domain of this function? Let's see, what x values does it go through? It doesn't go through 0, we have an open circle there. It goes through all the rest of the x values, all the way up to and including 24. So the domain would be, using interval notation, the open interval from 0 to 24 closed on the 24. And if you're using set notation, you could say 0 is less than x is less than or equal to 24. Now let's find the range. The range would be the set of real number outputs. So let's take a look at our graph. I see that we have points that go through a height of 0. We have points that go through a height of 2, and all the way up through almost but not including 8. So what we can do is kind of break this up into parts. So we have y equals 2, or anything in the interval from 2 to 8, including, let me go back. That was supposed to be y equals 0. Y equals 0, that was that lower one, or anything going from 2 to 8, including the 2, not including the 8. Okay, now let's talk about where this function is increasing or decreasing or constant. These are fairly intuitive. You have to be thinking about what the graph is doing as you move from left to right. So let's take a look at piece A. As we move from left to right, the y values are not changing, so the graph is constant. So the interval upon which the graph is constant would be the x values 0 to 8. Not including the 0, including the 8. Also, on the B section, it's constant again. The y values don't change. They're at a height of 2 the whole time. So it's also constant from x equals 8 to x equals 12, including the 12. Notice I'm only listing x values, not y values. It just, when you describe whether it's constant, increasing, or decreasing, you talk about the x values upon which that is happening. Now let's go with increasing. So you're looking for where your graph is going up as you move from left to right. So that would be part C. The graph is going up as you move from left to right. So the x values for that, starting at 12, but not including 12, and going to 18, but not including 18. So we have that open interval. And then decreasing would be as you move from left to right, you see the y values going down. So we see from x equals 18, including that, to x equals 24, including that. Now, not every graph is going to be increasing and decreasing and constant. Some graphs are just one or a mix of two of those things. Okay, let's switch gears a little bit and let's talk about some more function vocabulary. Even functions and odd functions. So if you have an even function, it's going to have symmetry about the y-axis. So an example of that might just be a very simple parabola. Y-axis symmetry. And algebraically, you can say that f of x is equal to f of the opposite of x. That means opposite x values have the same y value. So let's say this was the point AB. The opposite x value then would be the opposite of A, and it still has a y coordinate of B. They have the same y coordinate. In calculus, even functions come in handy, especially if you're taking the second term of calculus, integral calculus, which will be down the road for some of you, because there's something that you get to learn to do in calculus that has to do with finding the area under a curve. Let's say you wanted to find the area from here to here. Well, because the function is even, let's say that was -2 and that was 2. Because the function is even and you have symmetry, the area on both sides is equal, so you would actually only have to find the area from -2 to 0 and then double it. Or you could find the area from 0 to 2 and then double it. Odd functions also have symmetry, but the symmetry they have is symmetry about the origin. Here's an example. So in this case, if you have f of the opposite of x, it's equal to the opposite of f of x. And that means opposite x values have opposite y values. So suppose you have the point AB, and you find the opposite x value, that would be the opposite of A, it's going to have the opposite y value, opposite of B. Now, there are no functions that have symmetry about the x-axis. Let's picture this. Symmetry about the x-axis. Okay, so that fails the vertical line test. It's not a function. It's still a graph. You could call it a relation. It may even still have an equation. For example, in pre-calculus, we typically learn about sideways parabolas, and sideways parabolas might have an equation of the form x equals y squared instead of y equals x squared, but it's not a function. So we concentrate mostly on functions in this class. Let's see what else we have. Okay, I think this might be our last segment. Yep. Distance, midpoint, and circle. Okay, believe it or not, in calculus you do a lot with lines, and midpoints of lines can come in handy, the distance between 2 points can come in handy, and while we're doing those things we might as well talk about the equation of a circle. So suppose I have 2 points, 3, 4, and -2, 6, let's say. Suppose I want to know the distance between them. Remember, the distance formula is just based on the Pythagorean theorem. I'm not going to go into all of the theory right now since we're just doing a quick review. The distance formula is the square root of the change in x coordinates squared plus the change in y coordinates squared. And so if we want to find the distance, we would have the square root of the change in x coordinates would be 3 minus -2, and then that needs to be squared, plus the change in y coordinates would be 4 minus 6, and that needs to be squared. And then we simplify. So we have the square root of 5 squared plus -2 squared, and that would be the square root of 25 plus 4, and that would be the square root of 29, and we would just leave it like that. We would leave our answer exact. If it was possible to simplify that radical, we would. How about the midpoint formula? Let's say you want to find the point that's halfway between those. To find something that's halfway between, you average. So you average the x coordinates and you average the y coordinates. To average x coordinates, you add them together and divide by 2. And to average y coordinates, you add them together and divide by 2. So if we're finding the midpoint of these 2 points, add the x coordinates and divide by 2, add the y coordinates and divide by 2, and we end up with 1/2, 5. Okay, now let's visualize these 2 points on a graph real quick. 3, 4, just making a rough sketch. Here's 3, 4, -2, 6. Okay, now let's suppose that those were the endpoints of a diameter of a circle. So here's the circle then. Here's the diameter. What is the equation of the circle? So I'll remind you from pre-calc that a circle has equation x minus h quantity squared plus y minus k quantity squared equals r squared, where the center is hk and the radius is r. So the center would be the midpoint between those two endpoints of the diameter. And let's just say it's roughly here. My sketch was rough, it's not perfect, but we already found the point that's halfway between those two endpoints. That was our midpoint. So that's going to be the center of our circle. And then the radius is going to be half the diameter, so half the distance from the center to one of those 2 points. And we already found the diameter was the whole distance across, so then the radius is going to be half of that. So if we put those together, excuse me, we get the equation of the circle. This particular circle would have equation x minus 1/2 quantity squared plus y minus 5 quantity squared equals, and then for r squared, we square the radius, so square root 29 squared is 29, and 2 squared is 4, so equals 29/4. Okay, so we've gone through a whole bunch of little things, little but important things that are the foundation of your next math lessons. And for an assignment, I've made you a worksheet on vocabulary, notation, and more. Be sure when you turn this in that you also submit your notes along with your assignment and show that you've checked your answers. That's how you're going to get a mark of complete on your homework. You need to do all 3 of those things. To show you've checked your answers, remember you can put stars or check marks or happy faces or whatever your method is, highlighting, just as long as it's clear. Thanks, everybody.